All right. We're happy to have Lutz Warnke from Georgia Tech, who's going to talk about the Prague dimension of random graphs.
Okay, so thanks for the introduction and the opportunity to speak here. So everything I'm going to talk about today is joint work with my PhD student Hegur and undergraduate student Kaden Patton from Georgia Tech. And it concerns the so-called Prague dimension of random graphs. So somehow, what is the general setting here? So there are many different notions or concepts how we can talk about complexity of objects, complexity of graphs. We can think of them in terms of, okay, how efficient or compact can we represent them? Or we can take some decomposition perspective. How can we, how many, if we have a complex object, and how many smaller objects can we decompose it? And these previous two notions also give rise to some notion of a dimension. And so there are many ways to look at this idea, how complex are certain objects or graphs. And one notion of this was introduced in studied by many mathematicians in Prague in the 1970s, the so-called Prague dimension, which basically relates these three concepts. And this was introduced by Neshetrel, Poulter, and Lerder in the 70s. I'll tell you exactly what that is on the next slide, but for the moment, just imagine it's some notion of complexity. And one thing that's nice here about this Prague dimension is that there are many equivalent definitions that arise in different contexts. So there's a way to describe it or study it using algebraic techniques. There are combinatorial techniques with which you can look at the Prague dimension, and can also look at it through the lens of information theoretic techniques. So there are many equivalent definitions in different contexts, which indicates that this is quite a natural notion of dimension. So it's a good notion. And the general thing here is that in general, this parameter is NP hard to determine. So we cannot hope to always, algorithmically figure out what is actually the Prague dimension. So we have to resort to some kind of other ways to study the question. Either we want to maybe just approximate this quantity, or like we do here, we want to say, okay, what can we at least say about the Prague dimension for most graphs? Okay, so this will be what we're going to look at today. In some sense, we're going to try to study this Prague dimension parameter, which I'm going to introduce on the next slide, for random graphs. And we're going to try to understand what is this parameter for random graphs, and in particular, proving this conjecture for Röding-Cantor. What we're going to see is we're going to get some idea of what is the order of magnitude of the Prague dimension for almost all graphs. Okay, so this is one benefit of studying these parameters for random graphs. We typically immediately understand what happens for most graphs of interest. Okay, so here's one definition of many equivalent ones that I brought here for the talk of this Prague dimension. So one weird thing about the Prague dimension is somehow it's easier to define it for the complement of G than for G itself. And so the way to think about it is that I give you the graph G, and then what your goal is to find, first of all, a click edge covering of the graph. So you need to find a collection of clicks which contains each edge of your graph. And then once we have such a collection of clicks which covers all the edges, you want to color them so that no two clicks in your two collection receive the same color if they share a vertex. Okay, and the Prague dimension of the complement G is now if you minimize the number of colors you need among all such click edge coverings. Okay, so it's the way to think about it is you kind of want to minimize the number of colors over all possible click edge coverings of G. Okay, and if you prefer a little bit more abstract point of view on this, then you can also think of it in terms of the chromatic index. You can imagine that any click edge covering of a graph G, just imagine the clicks you can just imagine, pretend the clicks are hyper edges, where the vertices now of your click correspond to the vertices of the hyper edges. And then what you're really asking for is among all click edge coverings of G, you want to look at the minimum chromatic index. You want to color the edges of this auxiliary graph with the least amount of colors. Okay, I think it's time for an example to get used to this parameter at least once. So here's a small example that I prepared that we can look at. So here we have a bunch of edges. And so one way to get an upper bound here on the Prague dimension is, okay, so we first put down a click edge covering. So this is what I prepared here. So we have here these triangles and edges. The first thing to notice for the Prague dimension is that we don't have to, first of all, we can use clicks of different sizes, right? So here we use an edge Here we use a triangle, so that's okay. And also what you see here is that we don't insist on that all these cliques are edge disjoint, right? So here they can overlap in one edge. So that's also fine. Okay, so we first put down a clique edge covering. So the union of all these cliques we have here covers all the edges. And now we put down a coloring of these cliques, which I prepared here using 3 colors, green, orange, and purple. And so the key property is that whenever we look at 2 cliques here that share a vertex like this one here, then all these cliques here, they will be have different colors. Okay, so that's the key requirement. And so just drawing this picture proves to you that the Prague dimension of the complement of G is at most 3, right? Because I managed to find a clique edge covering and I managed to color it using 3 colors. So the question now is this best possible? Okay, and so in this example, there's an easy way to see that it's best possible. And the easiest way to see it is to just focus on this one vertex here and realize that in any possible clique edge covering of your graph, for this particular vertex, you need to have one clique which covers, say, this edge. You need a different clique which covers this edge, and yet another clique which covers this edge. And so now the point is that we require, right, that all the cliques which share vertex receive disjoint colors. So at this point, we see any clique edge covering of this graph needs to use at least 3 colors, because there will always be at least 3 different cliques which contain this one vertex. Okay, so in other words, you'll never be able to to color a clique edge covering using less than 3 colors, because for this particular vertex, no matter what you do here on the left-hand side, you need to use 1 color. For this edge, you need to use 1 color, and for this one, you also need to use 1 color, no matter which cliques you put there. Okay, so this proves that this guy actually has the complement of this guy has Prague dimension 3. And later on in the talk, it will be a little bit annoying to always talk about the Prague dimension of the complement of G. So let's just simplify our life, introduce some parameter which just depends on G. So we'll call this the, say, clique chromatic index, CC dash of G, so that we can just talk here about this quantity. Okay, so as you see, the definition of this parameter is quite involved here, but this will be the notion that is most useful for us in the proofs. Okay, so there are different definitions here of this quantity, but this is the one that will be most useful for us. And so now the conjecture of Freudian Cantor is that if we look at the random graph G and P, so we're looking at an n vertex graph where each of the n choose 2 possible edges is inserted independently with probability P. So for each edge, we flip a coin, whether it's there or not. Then for constant P, they conjecture that the order of magnitude of this parameter is of order n over log n. Okay, so the key point that it's sublinear. And to prove this conjecture, just to get used to these parameters like the CC prime and so on, this clique chromatic index, it's enough to show that this clique chromatic index of G and P is of order n over log n. So why is that? Let's just quickly think. So I told you that up here we were defining the Prague dimension of the complement of G. Okay, so if we turn this on its head, what we then have here is the Prague dimension of G and P is this clique chromatic index of the complement of G and P. But the nice thing about G and P is it has a very nice behavior under taking complements, because now instead of each edge being there with probability P, each edge is simply there with probability 1 minus P. And so for this particular conjecture, if we look at this thing here for constant P, well, if you have a constant P between 0 and 1, then 1 minus P is again a constant between 0 and 1. So it's enough to prove this bound here for constant P. Okay, so the good thing now about this perspective is that now for this conjecture is there's an easy lower bound. Okay, so as with many of these problems, one bound is a little easier than the other. One bound we might be able to guess in a nice way. And so this is the case here for a lower bound on this Prague dimension. And we're basically going to generalize this argument I used up here for arguing that this graph has Prague dimension 3. Okay, and so the way to think about it is we're just going to look at one vertex V, and that has a certain number of neighbors. Say we just take a vertex with the largest degree in our graph, say a big delta. Okay, and Moreover, assume that we also have some bound on the maximum click, say omega. Okay, so we think about the graph where the maximum degree is delta and the maximum click size is at most omega, right? So then very similar to up here, well, what is how many clicks are there which contain this vertex V? Well, in any possible click edge covering. Well, because the maximum click size is omega, that means that any click that you put down, like this one here, can use up at most omega minus 1 vertices in your neighborhood. Okay, each click can use up at most omega minus 1 neighbors in your neighborhood. Okay, and so we require that all these clicks, right, which contain this vertex V, receive different colors. So any click that you put down can use up at most omega minus 1 vertices over here. So overall, to actually cover all these edges here from the neighborhood of V, you need at least delta over omega minus 1 clicks, no matter what you do, because any possible click can kind of eat up at most omega minus 1 vertices from your neighborhood. Okay, so what this argument tells you is that the click chromatic index is at least the maximum degree of your graph divided by the maximum click size minus 1. Okay, by this argument that in any possible click edge covering here, every vertex is contained in at least so many clicks, and we know that all these vertices contained in one particular click need to receive different colors. So that's where this lower bound comes from. And just take my word for it, things like the maximum degree and maximum click size, we understand this extremely well for a random graph. So the maximum degree will be very close to n times p, and the maximum click size will be very close to log n. And so that's where this lower bound comes from here, from Viridian Cantor. Okay, so that's the easy lower bound, and our task will be to establish a similar upper bound. Okay, so I should mention, so I prefer, like, if there are any questions, you just ask them directly during the talk. I think it's best we clarify them right away before ending all the way to the end. So if there are any questions here about what the conjecture is and where the lower bound comes from. Okay, so so what is the main result that we obtained? So basically, we prove this result that this click chromatic index here is of order n over log n for constant p. So that's our main result. We show that this holds with high probability. So this means that with probability tending to 1 as the number of vertices tends to infinity. And as discussed, this exactly verifies here this Prague dimension conjecture of Viridian Cantor, because we know that the Prague dimension of GNP is just this click chromatic index of the complement of GNP, and 1 minus p is again a constant, so we get this nice bound. Okay, so that's about like what we can prove. And of course, this is kind of a simplified version of our main result. So there are a bunch of different extensions. Let me just mention here 2 of them maybe. So here I stated the result for constant p. So here for this click covering a chromatic index, we can also allow for p to go to 0. So when the graph gets sparser and sparser, fewer and fewer edges, in that case, the bound that we get is of this form up to constant factors np over log n to the base 1 over p. So we kind of match up to constant factors this lower bound that we discussed here. Another thing which I find interesting, where I'd be interested to know if it has further applications, is so for our proof technique here, we do not need to insist that we look at click edge coverings. So for click edge covering, we just assume that the collection of clicks we look at, each edge is contained in at least 1 click. But our proof also allows us to prove the same for click edge packings. So where every edge is contained in exactly 1 click. Okay, and so we can also prove this kind of result, and it would be kind of interesting to know if that extension has some further applications or on other parameters maybe. Okay, so let me just mention here, like if I would be forced to tell you 1 point, what is the main difficulty here? The main difficulty is that we need to use, to get this result, as you might see here from this lower bound, the only way in this setup we can get this extra log factor, or where this term comes from, is we use many large clicks of size order log n. That's the only way we can bring this parameter down from much to n over log n. Okay, and so the main point is that we have many tools and techniques how to deal with graphs and with many graph or hypergraph problems, and they were very good when things have constant size. When the objects we are looking at do not depend on the number of vertices. And here we really need to look at these very, very large cliques, and that causes some difficulties in the proofs how to handle this. So that's kind of the main issue. We need to use many cliques of large size. Okay, so if you see this for the first time, I think it's again a good point to ask. So why should we really care? What is the motivation here? So maybe motivation number one is we have a parameter like the Prague dimension, which is still not so well understood. So it's very natural to study it for random graphs. And the reason is this result up here, if you instantiate it for p equals to 1/2, well, what does it tell you? If you look at the random graph with edge probability 1/2, that exactly gives you a uniform distribution over all graphs with n vertices. So if you prove such a result like this one here, which says with high probability you get certain bounds, then that tells you that almost all n vertex graphs satisfy this bound here. Okay, and the significance is that there are graphs where in the worst case here this parameter, this click chromatic index, can be of order n. So what this result basically is telling you is that for almost all graphs, you're very far away from this extreme behavior. You're significantly smaller than this worst case behavior. Okay. The second motivation I want to mention here, it comes from this connection to covering and decomposition problems, which are really nowadays all over combinatorics, which many really exciting and great results that are being proven. The main difference here is again the fact that typically we tend to decompose things into objects of constant size. So here we could decompose the edges into cliques of constant size, but for our problem that's not enough. For our problem we need to really decompose things into growing cliques. Okay, so that kind of gives an interesting twist on this classical idea. And the third motivation, which is maybe how I arrived at this problem, is kind of in terms of also interesting proof techniques, because to prove the result, so we need to prove an upper bound on this parameter. To do that, we effectively need to construct a click edge covering, and we also need to construct a coloring of this click edge covering. Okay, and both of these steps, we're going to use algorithmic tools. In fact, we're going to use randomized algorithms to achieve these goals. Using actually two different paradigms for designing randomized algorithms, and I'll say a little bit more about that. So these are the, I would say, three motivating factors here why one would want to study such a problem. Let me just say one or two words about related parameters and previous work. So so prior to our work, people have studied variants of this problem. So of course, if you see this complicated definition of a parameter, maybe it's easiest to see here if you look at this more abstract perspective, where you think of this as a like a hypergraph edge coloring problem, right? We take the minimum over all click edge coverings of G, where we think of each click edge covering as a hypergraph. And we think of here of the chromatic index, the least number of edges, least number of colors we need to color the edges. Then you would immediately say, why do we put there this chromatic index? We can put other parameters there. It's quite natural to study other parameters, and this is exactly what was done previously. So instead of looking here at the chromatic index, people have looked at the size. Okay, so you want to look at what is the smallest size of a click edge covering of your graph GNP. So I think there was also some previous work by, I should know this, I think by Bolobash, by Joel, and by Douglas West, and so on and so forth. So there was some previous work on this parameter, and eventually the order of magnitude was nailed down by Alan Fries and Bruce Reed in 1995, that the the smallest size of a click edge covering is roughly n squared over log n squared. And then in some later work, Feridian Cantor, they studied also what happens when you look at the maximum degree, and there they prove that it's n over log n. Okay, and of course, the maximum degree here in this abstract setting, that's a lower bound on the chromatic index. And that was, I think, also one of the motivations. Like they originally wanted to understand the chromatic index, and then I think they managed to understand what the maximum degree is, which is like very close to the chromatic index, but not quite there. And that motivated also their conjecture. Okay, and I should say that our result here also reproves all of these results, again allowing for p tending to 0 and also for packing variance. In fact, what's interesting to me is that in some sense we find a click edge covering which satisfies all these properties simultaneously. So we find a click edge covering which is of this size, has this maximum degree, and has this chromatic index. So in that sense, it's like weakly pseudo-random click edge covering, or I don't know how one would want to call it, but we minimize all these parameters up to order of magnitude simultaneously, which is nice. Okay, I'll wait a moment if there are any questions.
Yeah, Lutz, Joel here. If I can ask a question about the constants, let me take p equals a half. We know the clique number is 2 log n, base 2, but cliques of size bigger than 1 log n are particularly hard to deal with. What size cliques do you actually use in your algorithm?
So I think in the end we ended up using like I guess a tenth or something like this, but
tiny.
Yeah, we could in principle, I think, if we work harder, maybe 1 minus epsilon or something, but not all the way up. There's some the concentration causes some problems if you go beyond that. They're like to prove throughout our randomized algorithm that everything stays concentrated. It's easier if you have more of them. So
yeah, okay.
Yeah, but I'll later say something about the constants, which I think is very closely related to your question. Basically, if this is the right answer, and I can already tell you that, for example, for p equal to 1/2, this is not the answer. It's certainly at least off by a factor of 2, but we don't know exactly. But one can get a better lower bound, surprisingly, maybe.
Okay.
Let me just mention here, I'll mention later because you like these random graphs. Basically, one can do a very complicated union bound over all these click edge coverings which satisfy certain properties to do a little bit better, but it's a not so nice calculation. Okay, are there more questions, comments? So, okay, so let me otherwise say a few words about the high-level proof strategy. Okay, so we have this parameter where we need to, if we want to get an upper bound on this parameter, we need to find first a click edge covering, and then we need to color it using very few colors. Okay, and so each of these steps we're going to try to approach algorithmically. So we're first going to try to find a click edge covering of the graph, and there, intuitively, I'll try to say a little bit more about on the next page, but maybe not too much. So there we use a so-called semi-random nibble type algorithm. But that's a fancy word here for abstractly saying is that we construct the click edge covering in small steps in some sense. So each time we add a certain number of clicks to our collection, then we make a break, then we again add a bunch of clicks to our collection, then we again, and so on and so forth. Okay, so that's kind of how we will do that. I'll say a little bit more about that, but basically we add these clicks in chunks. We build up this collection of clicks in chunks. We don't just add one click at a time, but we add many clicks in each step. And once we have this click edge covering, the high-level strategy is to basically color all these clicks using disjoint color sets. Okay, so it turns out that we can just bound the total number of colors we need, the click chromatic index of this collection, just by summing the number of colors we need for each of these sub-collections. Okay, so if you write it in this click chromatic index language, then the click chromatic index of the entire collection is the sum of the chromatic index of the sub-collections. Okay, And so our goal will then be to color these sub-collections using as few colors as possible. And there, we're going to use a random greedy algorithm, where basically you allow yourself a certain number of colors, and then you go through the edges in some random order and assign these colors. And that way you get a valid coloring using not too many colors. Okay, so this is just the high-level picture. Step 1, we find one particular click edge covering. In step 2, we show that we can color it using not too many colors. So let me maybe just give you a glimpse of how step 1 works, and then I'll spend most of the time on step 2 because that's where the main innovation lies here of our work. So for step 1, remember what we have to do is we start off with a random graph GNP, and we need to find a click edge covering of the edges of our graph. And so the way we're going to do it is we start off with the complete graph GNP, let's call it G0. Then we're going to take out a bunch of clicks from this graph and add it to our first set, of clicks C0, say. Okay, then we remove all these clicks from this collection, getting a new graph G1. And from this, again, we're going to remove certain clicks, and then we're going to continue. And so how do we do this removal step? Well, basically, we put all clicks of a certain size into a bag, and then among those, we're going to take a random sub-collection of a certain size. Okay, so we start off with our random graph GNP. We delete, or we take out a certain number, a random number of clicks, put them into our bag, remove all edges that are in here, and then continue iterate. Unfortunately, we cannot do that forever, or we don't have, or luckily we don't have to do that forever. It's enough if we repeat this so many times that at the end the graph is very, very sparse. So very sparse means here that for example, for constant p, this means that you have like n squared over log n to the 4 many edges left. So it's not just epsilon n squared edges left, but really substantially less. And then we do something very simple. We just put all the remaining edges of this final graph into this one bag CI. That will be fine for us. Okay, so we start off with the complete random graph. We take out random clicks for a while until the graph is very, very sparse. And then we just put all the remaining edges into this one bag. And so that has a lot of nice properties, this construction. And so with some technical work, one can make rigorous the idea that if you look at the random graph GI here in this sequence, it looks like, or has many properties like a random graph. So if you look at the certain properties of clicks, they very closely resemble the properties of a random graph GNP. And so the cartoon version of it is something like that pi decays exponentially like e to the minus I. Okay, so it starts pi is something like p times e to the minus I. Okay, I'm simplifying here a little bit, but that's kind of the cartoon version. You should keep in mind that this thing gradually gets sparser and sparser. Okay, and justifying this key property requires some extra technical bells and whistles. So I was cheating here slightly. We don't just randomly delete clicks. We also randomly delete certain edges. It has some technical advantages. I don't want to go too much into details here. But the main story here is that we randomly delete clicks for a while. The remaining graph, the leftover graph, always stays pseudo-random. And that's how we construct our collection of clicks. Okay, so that's, I think, a very natural strategy from a random graphs perspective, how to find one such edge decomposition. And now the question, of course, is how do we color this? How do we color this? Because otherwise, if we cannot find a way to efficiently color this, we're not in so good shape. And so now comes this random greedy coloring step that I described. So, of course, we bound this click chromatic index parameter above by the number of colors we need to color this particular collection of clicks. And the way we do it is, as I described earlier, is we're going to give just disjoint colors to each of these sets. Okay, so we write here, total number of colors is at most the sum of these individual colors. Here, I immediately split up the sum into those guys where we take out random clicks, and the final set because the final set is a little different, right? The final set that does not contain large cliques, those contains just edges, right? Because we said, oh, we decompose until the graph is very sparse and we put all the edges into one bag. And so now look, the last, let's focus maybe first on the last set here. So how many colors do we need to color these remaining edges? Well, the nice thing is that, you know, if we just color edges, then we have some very simple bounds for how many colors we need to color this thing. All right, so there's like a Wiesing's theorem, or you can just use a trivial greedy algorithm will tell you that you can color the edges of this thing using twice the maximum degree. Okay, using twice the maximum degree. That's a very simple bound. And so the main message here is basically it's up to constant factors the maximum degree. Okay. And if you want, you can improve this constant too, right? You could remove this here and just write +1 here, but we don't care about constant factors here, so let's just forget about it. Okay, so the main point is here we have maximum degree. And so that lets us kind of make this dream statement. So what if we could also get such a bound? What if we could also get such a bound here for coloring the other collections where we color these large cliques, right? So here we'd get maximum degree for free by Wiesing, but we would want to maybe the world is nice and we can also color these other collections using order of magnitude times the maximum degree many colors. Okay, that would be our dream statement. There's some motivation for this, which I might expand a bit more on the next slide. But if your graph would have only cliques of constant size, then there would be ways to justify this immediately. So there's some very nice result, I think, from the late 80s by Pippinger and Joe Spencer, which allow you to color hypergraphs that are pseudo-random, where the degrees are pretty regular and the codegree is not too big. Then you would be able to color this thing using, say, 1 + epsilon times the maximum degree. But we're not in that situation. We're not so lucky because our hyper edges will be extremely large here. They can be of order log n. So that result does not apply. But let's maybe tag along for a moment. Let's just dream that maybe we could get such a bound. Maybe we could get such a bound. Then if you do the calculations, you get some bound which looks roughly of this form. So maybe what I can say about is, okay, let's maybe look at first here the last term. What would be the bound we get here for the final set? Well, we said that we can color this using twice the maximum degree. And in this cartoon version here, the edge probability pi scales roughly like p times e to the minus I. So for coloring this final set, we need so many colors, np times e to the minus I. So if we can make I sufficiently large, okay, if we can make I sufficiently large, this term will be awfully much smaller than what we're aiming at, this np over log n. Okay, just take I some, I don't know, some big constant times log n or something like this, and then this would be fine. Okay, so by making I large enough, the last term we don't have to worry about. And the other one, well, if you look at the construction we're looking at, we would get something of this form, the sum of npi over log n to the base 1 over pi. Well, where does this roughly come from? So one intuitive way to see this maybe is the following, that I told you that we can actually get disjoint cliques, right? And so if the cliques were disjoint, well, this graph GI, if it's a random graph G and P, then it has roughly maximum degree n times pi, and the cliques of that thing have roughly size log n to the base 1 over pi. So maybe this is roughly what you would expect from your hypergraph. Anyway, the main point is that we have a big sum here, but you should not be scared. Because these edge probabilities pi decay exponentially, so the main contribution comes from the first few terms. So in particular, if you just plug in I equals to 0, then you see that it's exactly what we want. Okay, it's exactly what we want. So the main message I want to bring across here, if we could prove this result, that we could bound the chromatic index of this subcollection using the maximum degree, then we would be in business, then we would get the result. That's the main message of this slide, okay? So in other words, we've kind of reduced the problem now to figuring out if this is true. I think I wanted to expand on this a little bit more. Yeah, so because this is, I think this here is kind of at the core of the problem. I think this particular point was holding back progress on the problem previously. So let me maybe say a few more words about this. So the main reason why this was challenging was, as I mentioned, because the clicks have very big size of order log n. If they were of constant size, then this result here by this previous result by Pippinger and Joe Spencer, that would be enough. So what their result says is that you can color the edges of any hypergraph H that is K uniform for constant uniformity, that's approximately regular and with small codegree. You can color that using 1 plus epsilon times the maximum degree many colors. Okay, and so basically we satisfy basically these second two properties, approximately regularity and small codegree for the CI. Well, where does that come from? Well, that comes basically from the following, because we do this random construction here, right? So each time we take out a random collection of clicks, and I promised you that when we do this sparsification step, we stay pseudo-random. So if you take out random clicks from something that looks pseudo-random, then just take my word for it. It will also have lots of nice pseudo-random properties. I mean, we're using randomness everywhere. So yeah, that should be fine. So the main obstacle here is this K uniformity assumption. Okay. And so that's now a severe problem that we're facing here. And one might believe it now one is stuck. Okay. And in particular, this result here of this Pippinger-Spencer type, I know that it cannot be extended beyond order log n. So there are examples where if you look at some big constant times, where k is some big constant times log n, then you cannot get here a 1 plus epsilon here in this upper bound. This actually has to grow. Okay, so that's another technical obstacle. Okay, but look, what this result says, it says for any hypergraph H. But that's not what we're really using, or the way around it is to say the following. Remember, how did we get at these clicks? We were taking a random so we're looking at all the clicks in here and then taking a random subcollection of clicks. So we don't have to prove our result for all hypergraphs H, but we can still exploit the fact that we're sitting inside a random proof environment. These clicks, this collection CI of clicks that we're looking at, that's actually still random. And so we should exploit this randomness in our proof to sidestep this problem. And this is exactly what we do. We use the fact that we generate the set CI at random in order, in the end, to relax this assumption that K is constant in this result to allow for clicks of size log n. And so that's how we get around this technical problem, by saying, we don't have to prove something for any hypergraph H, but only for these hypergraphs which come from a certain random construction, and then we're in business. And that allows us here in the end to push through this kind of argument. So because I think this should have other applications, let me maybe state a precise version of what kind of result we can prove to give you a feeling for what is going on. So this is the kind of result we can prove for these hypergraphs. So we're given some hypergraph H, which will be K uniform. Okay, so every edge contains K vertices. And we have these three assumptions. So it's the edge uniformity. The key point is now we can allow for the edge uniformity between 2 and a constant times log n. And then we have these two extra assumptions. We want it to be regular and have small codegree. So regular means that, up to some small polynomial factor, they're equal to d. And the codegree here is some polynomial factor smaller than the degree, basically. And then what we can show is that if you take a random subhypergraph of H, which contains a certain number of edges, so not too few edges and not all of them, basically, then with high probability, to color this random subhypergraph, you basically need the maximum degree of this hypergraph many colors times some extra factor of 1 plus delta, where here we have some explicit expression on delta in terms of here this constant b from the edge uniformity and this sigma here from this error term. Okay, so that's really a result we can prove. There's not really anything hidden here. And I think there are two attractive corollaries here, which one should keep in mind. So one is, what happens if you apply this result when K is little o of log n? Well, remember here in this result, how did the dependence on K go in? It was here in this constant B. Okay, so that means that you can, if K is little of log n, you can make this constant as small as you want. That particularly means that you can make the delta as small as you want. So, okay, so if K is little of log n, you really can show that the chromatic index is at most 1 plus epsilon times the maximum degree. So you really recover this Pipping or Spencer type result. And for our purposes, we have to apply this result where K is a constant times log n. So RB will really be an honest constant. So this delta term will also be an honest constant. Okay, so we get that the click chromatic index is at most a constant times the maximum degree. And that's what we apply. Okay, so this I think is I feel quite a nice statement for these hypergraphs with growing edge sizes, and it will be very interesting to see if this kind of result has some further applications in other contexts. I think results for the click chromatic for the chromatic index of hypergraphs with growing edges, there seems to be very little known. And so it'll be interesting to see if this kind of also random results have some other applications. I think this would be a good point maybe to ask questions about the statement. Otherwise, I would try to say 1 or 2 words about how we prove such a statement. Okay, so the way we want to prove this is using, again, algorithmic approach. So here we want to use a random greedy algorithm, which uses at most 1 plus delta times K times n over n colors, where this quantity here, if you check things, that's roughly the maximum degree, okay? So I'm simplifying here slightly for the sake of presentation, but basically, we're going to use an algorithm which has a certain reservoir, a certain number of colors it's allowed to use, and we're going to show that using that number of colors, it will do the job. Okay, it will never run out of colors in its execution. And the way we analyze it is using the so-called differential equation method, which allows us to relate the behavior of this random greedy algorithm to a certain system of differential equations, so we can transfer properties or the behavior of the differential equations to the algorithm. So this is some method which was, I think, in the context of computer science, was first introduced by Karp Sipser, later in combinatorics context, very much popularized by Wormold, and also more recently, some very powerful developments by Tom Bowman and co-authors. So let me just show you how simple this algorithm is that we use, okay? So we use this very simple coloring algorithm, and I should highlight that this is actually different than what was used in the Pipping or Spencer proof. They used a different approach than this greedy algorithm. Okay, so what is the most simplest greedy algorithm you could imagine? You give yourself some set of available colors, and now in each step, you look at one edge. So because we're looking at the random subhypergraph, you can just pretend that this edge was generated at random the moment you look at it. And then we color this edge with a random available color from Q. Okay, so at each time in your algorithm, right, because you already colored certain edges, at each vertex, or rather at each edge, you only have a certain subset of all these colors that are still valid. So that if you use this color, it will not give you a conflict. Okay, and so for each edge, the number of possible colors you can use shrinks over time. And from that set of available colors, you each time choose one uniformly at random. And what our claim is, under the assumptions from the previous slide, that if you plug in this particular set of parameters, where Q is approximately 1 plus delta times the maximum degree, then with high probability, your algorithm will succeed. It will never run out of available colors at any edge that you look at. So whenever you look at an edge, there's at least one color you can use. Okay, and that then means that, yes, your algorithm successfully colors everything. Because at each step, whenever it puts down a color, that will be okay. That will not violate any constraints. Okay, and so what kind of properties go into the analysis here? Let me just give you kind of a glimpse. What are the kind of statements one needs to prove here? So as we already observed in the discussion here, to show that this algorithm succeeds, the key thing to show is that at this step here, when we actually color an edge, that we always have some colors left to use. So in the algorithm, it's very natural that we want to keep track of how many colors can I still use at this particular point. Okay, so this is what this variable QE will do. It counts the number of available colors for E after I steps. Okay, and so what we basically show using this differential equation method, that this the number of available colors behaves roughly like this. Okay, so the key point is on the left-hand side, we have a random variable, and the right-hand side, I wrote down some deterministic quantity. Okay, and so what this method allows you to show is that the random variable always stays very close to this deterministic quantity that's much easier to understand. And that scales something like this: the total number of colors times some rescaling factor. Okay, so that's how this goes. And I think we have a few minutes left. Is that correct? Or so let me maybe just, because for those of you who are interested in the audience, just mention that you could ask the question, okay, once you have this formula, now you can intuitively see why we can allow for so large edge sizes. Because if we look at this quantity here and we plug in that k is at most b times log n, then you'll see that throughout the behavior of this algorithm, this quantity here, that always is much bigger than 1. Let me maybe not do the calculation here, but it turns out that if you plug in here this k at most b log n, then the way we set up everything, this number always stays very large. And that means that at any possible edge, the number of available colors stays large. Okay. And the way one justifies this method is using tools from probability theory, martingale methods, and so on and so forth. I don't want to go into details. I want to mention that, that's all I really wanted to say about the proof here. I wanted to say at the end a little bit about what we don't know. So in particular, what we don't know about the asymptotics of this click chromatic index. So, what we proved in our bound is that for constant p, we get n over log n. And at the beginning of the talk, I showed you this simple lower bound, which was just using the maximum degree and the maximum click size. That predicted something like np over 2 log n to the base 1 over p. And now you could ask, is this the truth? Is this the truth for our parameter? And maybe for some while I thought that this is true, because in many of these cases, the lower bound is very simple. The upper bound requires some work. But then we realized that you can actually improve this bound a little bit. And so, for example, for p equals to 1/2, we can add an extra factor of 2 to this bound. Okay, so what this bound here is saying is the same bound as above here, plus some extra factor 1 plus f of p for some f of p bounded away from 0. And this guy is actually equal to 2 for p equals to 1/2. So you can do twice as good as this lower bound. The proof is more complicated. Basically, what you have to show is that any click edge covering with the desired properties, if you do a union bound of all of those, you'll see that there are too few of them to actually appear in your random graph. So the probability that any of them appears, that probability will tend to 0. All of them that give a smaller bound. So yeah, so I don't know. I think maybe I'm willing to maybe believe that maybe this is the true answer, but it would be very interesting to see if someone can either prove this or disprove this. I think any of the two would be interesting, because it would give us some new idea about this geometry of click edge coverings. Okay, so let me maybe just briefly summarize. So we're looking at this complexity parameter Prague dimension. And so what we proved is that this Prague dimension is typically of order n over log n for constant p. This was verifying this conjecture of Freudian-Cantor regarding this pretty old parameter that was introduced in the 70s by Riddle, Neschetschel, and Pultrell. The proof used two nice random greedy approaches to once find the decomposition of the edges into clicks and then coloring them. And the main new tool, which I think would be very nice to see more applications, is to extend this Pippinger-Spencer type result to a random setting. And in this random setting, we could allow for edges of not of constant size, but of growing size. And that I really would like to see some more applications of. And the obvious open questions here is, can you now figure out the asymptotics of this parameter? In other words, can you figure out here what this implicit hidden constant here is? And that's exactly what I was hinting at here. Maybe this here is the true answer. Be interesting to understand. And with that here, I'll stop and open up for more questions.
Thank you. So any questions?